In this video, we're going to be looking at a technique to help us find zeros of a function, and it's called Newton's method. Let's say we have an example here. A car dealer offers to sell you a car for $18,000 or for payments of $375 per month for 5 years. The monthly interest can be calculated by solving this equation. Notice, solving this equation by the techniques that we've learned previously in prior math classes, it would be very difficult. But you notice that we are trying to find where this graph crosses the x-axis because it is set equal to 0. Let's take a look at the graph. Here we can see the graph crosses just before 0.008. So that would be the solution to this equation. But again, this would be very difficult to solve algebraically. We're going to look at this technique, which is called Newton's method, to help us find these x-intercepts or zeros of a function. And this is the idea behind Newton's method. I'm going to first of all estimate where I think the graph crosses the x-axis. Now this is going to be done several different ways. We could possibly use the intermediate value theorem to find a value where the function is negative, find out where it's positive, make sure it's a continuous function, and we would have an interval where we knew the graph crosses the x-axis. We could also possibly just look at the graph just to get an estimate of where the graph crosses the x-axis. Now for demonstration purposes, I am going to choose a value that's quite a distance away from where I can see it actually crosses the x-axis, so I can show you this technique, Newton's method, and how it works. So first of all, let's say I choose the value 2.5. I say that's where I think my 0 is to this function. We can see it's much closer to 1. However, again, for demonstration purposes, I'm going to choose a value a little bit further away. If we were to choose 2.5 and then create the equation of the tangent line for that point, we can find this value because this is our function that we're working with, y equals f of x. So we could find this value here. This would be x sub 1 comma f of x sub 1. So that we'd be able to find. Now to find the equation of this tangent line, we could use the point slope form of a line. We know that y sub 2 minus y sub 1 equals m times x sub 2 minus x sub 1. Y sub 1 can be found just by plugging x sub 1 into the function. The slope of the line can be found by plugging x sub 1 into our derivative. That would find the slope of this tangent line. Then we would have times our x sub 2 minus x sub 1. So you can see all of these values except for y and x sub 2 we can find. Now look at down here where our tangent line crosses the x-axis. Notice that would be a better estimate than my first original guess. And this is the whole idea behind Newton's method. We are going to take the equation of this line that we just found. Let's say I solve for y, so we'd have y equals f of x sub 1 plus f prime of x sub 1 times x sub 2 minus x sub 1. And where this line crosses the x-axis, y is 0. So let's plug in 0. And then we could solve for x sub 2. And this would be x sub 2 right here, that value. And we could use that as a better estimate for where this graph crosses the x-axis. However, if we wanted to get a better estimate, we could take this value x sub 2 and create the equation of the tangent line at that point. So let's say I take that point and now I create the equation of this tangent line. So now we would repeat this process that we did up here, and we could find where this line crosses the x-axis, and let's call that x sub 3. So that would be our x sub 3. And that would be a much better estimate for the equation or the value for where this crosses the x-axis. And if we repeat the process again, you can see the equation of the tangent line for that next value would give us an even better estimate for our 0 to the function. So we're going to generalize this process. So let's go back up here to where we were trying to find x sub 2, the first place that we crossed the x-axis. So we're going to solve that equation for x sub 2. So we're going to subtract f of x sub 1 then we will divide by f prime of x sub 1. And solving for x sub 2, we would have x sub 1 minus f of x sub 1 divided by f prime of x sub 1. So that's how we would find our x sub 2. Now, if we repeated this process to find x sub 3 and x sub 4 and so on, we would have x sub n plus 1 equals x sub n minus f of x sub n all divided by f prime of x sub n. And that is Newton's method. That's how we're going to find where our tangent line crosses the x-axis to give us an estimate of the 0 to a function. And we can repeat this process as many times as we like to get a more accurate answer. And we'll discuss how do we know when to stop? What degree of accuracy do we need? Starting with x sub 1 equals 2, find the third approximation, x sub 3, to the root of the equation x cubed minus 2x minus 5 equals 0. So our initial guess is given to us. We're told x sub 1 equals 2. That's our initial guess. Now the function that we will be using is y equals x cubed minus 2x minus 5, and we know we will need the derivative of this function, so we will find that now. And now we will apply Newton's method. Now, in general, we know that Newton's method is this. So we already have our x sub 1, our initial guess. So we are now going to be looking for x sub 2. So x sub 2 equals, this would be our x sub 2. So x sub 1, which we know is 2, minus f of, and again, x sub n in this case is x sub 1, so we would have f of 2 all divided by f prime of 2. We can see that's 2 minus. If we plug 2 into our function, here's our function here, we'd have 8 minus 4 minus 5, which is negative 1, divided by f prime of 2. Here's f prime of 2. So if we plug 2 into that function, we'd get 12 minus 2, which is 10. So we would get 2 plus 1/10, which is 2.1. Now we're going to look for x sub 3, because it says find the third approximation x sub 3 to the root of the equation. X sub 3 equals x sub 2, so that would be 2.1, what we just found, minus f of x sub 2 divided by f prime of x sub 2. So we would have 2.1 minus, now we're plugging 2.1 into the function, and then we're going to plug 2.1 into our derivative. And an approximation would be 2.0946. So that's our decimal approximation for the root of the equation x cubed minus 2x minus 5. And let's take a look at the graph, remembering that we're saying it should be around 2.09. And you can see the graph crosses just beyond 2, and we said 2.09. Use Newton's method to find the sixth root of 2 correct to 8 decimal places. Well, when we're using Newton's method, we typically have some function, y equals f of x, and then we use that function and its derivative when we set the function equal to 0. So let's try to create a function from this scenario. Let's say the sixth root of 2 equals some number x. We could then, this is the same as 2 to the 1/6 power, so we could take and raise each side to this power of 6. So we would have 2 equals x to the 6th. And so if we subtracted 2 from both sides, we've created an equation that is set equal to 0. So our function would actually be x to the 6th minus 2. And so f prime of x would equal 6x to the 5th. So now we can apply Newton's method. Now thinking about the sixth root of 2, we would probably guess that, well, it's going to be pretty close to 1. So let's make our initial guess, our x sub 1 equal 1. Now this says we're going to find this correct to 8 decimal places. Now the idea behind the accuracy is that when we start using Newton's method, we're going to get some decimal approximations, and we're going to look to see when 8 decimal places stop changing. Then we know we have a degree that's accurate to within 8 decimal places. So let's apply Newton's method first. So x sub 2 would equal 1 minus f of 1 divided by f prime of 1. So here we would get 1 minus, and our function, we're plugging in 1, so we'd have 1 to the 6th minus 2, all divided by 6 times 1 to the 5th. So I'm going to have to write that down here. Don't have enough room there. So if we looked at the decimal approximation to this value, we would get 1.16667. Now we would repeat this process. We would find our x sub 3. We would take our x sub 2 minus our f of x sub 2 divided by f prime of x sub 2, and we would get our x sub 3 value. So this is going to be left as an exercise, but I'm going to list the values that you should get. Then we would use that to find our x sub 4. This is an iterative process, so we have to have the prior answer to help us find the next answer. So then for x sub 4, we would have, and again, this is an estimate. For our x sub 4, so these shouldn't be equal signs, they should be approximately equal to. And we can see here we are not changing only to the hundredths. So we're only accurate to within the hundredth spot here. So we need to keep going. So if we found our x sub 5, and you should practice this to verify this. Now, again, we're going to compare this with our x sub 4, and we see we're not changing up through 4 decimal places. So we are going to have to repeat this process. So if we find our x sub 6, we would have 1.224625. So we now can conclude that since 8 decimal places have not changed, that we have found the correct answer to 8 decimal places, 1.1224625. And you could verify that with your calculator. There's the graph of our x to the 6th minus 2. And you can see where it crosses the x-axis. We said about 1.122, and that agrees. Find correct to 6 decimal places the root of the equation cosine of x equals x. Now, think about solving this equation. If you were to try to solve for x, we have a trigonometric function and an algebraic function. So algebraically, it'd be difficult or impossible to solve this equation. But we can actually use Newton's method to help us solve this equation. We are actually going to find the value where the cosine of x equals x using Newton's method. So first, let's think about our initial guess. If we were looking at the cosine curve and y equals x, there's our two functions. We're trying to find where those two intersect. Now we know here this value where cosine crosses the x-axis is pi over 2, which is approximately 1.57. So we know the value of x, which satisfies this equation, is going to be someplace around 1. So that's what we're going to use as our initial guess, x equals 1. Now, remember, when we use Newton's method, we're looking at where an equation equals 0. So we're going to subtract x over to this side. And then we can say the equation that we are working with is the cosine of x minus x. And we're trying to find where it crosses the x-axis. That's why we're looking for this here, where it equals 0. But the function that we're going to be using is this, and its derivative would be negative sine of x minus 1. We said our initial guess is 1. So to find x sub 2, we would have 1 minus f of 1, all divided by f prime of 1. So we would have 1 minus cosine of 1 minus 1, all divided by f prime of 1. So we would have negative sine of 1 minus 1. Now, if we evaluated this, we would have our x sub 2, and that is approximately repeating this process to find our x sub 3. And again, this is left to you as an exercise. You're going to be applying Newton's method to find these values. We can see we're only accurate to within a tenth, so we need to repeat this process. So using Newton's method, and again, we're not accurate to within 6 decimal places, so we would apply Newton's method again. And there we have our accuracy beyond 6 decimal places. So here this gave us an accuracy to within 6 decimal places because our x sub 5 is not changing all the way out to 8 decimal places. There's the equation of the cosine of x minus x. And we can see that the solution is around 0.073 as we had found.